Hey and welcome! So, if you think y equals mx plus c is the be-all and end-all of describing a line, you're in for a treat. Today we're jumping into the vector equation of a line, which is this incredibly powerful way to define any line. Not just on a 2D page, but, anywhere in 3D space. Let's get into it.
So here's our game plan. First, we're going to kind of rethink what a line is from the ground up. Then, we'll build the vector equation using this really simple idea of a two-part journey. After that, we'll make it official, solve a few common problems, and even see how to unpack it into another form. And then, of course, we'll hit the practice zone to make sure it all sticks.
All right, first things first, it's time to step away from the comfort of y equals mx plus c. I mean, it's been great for us, but we're about to unlock something way more flexible and, honestly, way more powerful.
So, let me just ask you this. What two things do you absolutely fundamentally need to pin down one single unique straight line? You definitely know one way to think about it. But what if there's a more, intuitive way? Okay, so on the left, this is what we're used to, right? The Cartesian equation. It's perfect for a flat graph. But trust me, it gets really messy when you try to take it into 3 dimensions. Now look at the right, the vector equation. It probably looks a little weird at first, but this one little formula, r equals a plus lambda d, it works perfectly in 2D and 3D. That is the power we are talking about.
So how do we even build this thing? Well, the absolute best way to get your head around it is to think of it like you're planning a trip.
I mean, think about it. If you're giving directions, you need two things, right? You need a starting point, a place to begin, and you need a direction to travel in. It is exactly the same for a line in space. We need a known point on the line, and we need a vector that tells us which way the line is going.
And this quote just nails it. The vector equation is really just a set of instructions. It's a recipe that tells you exactly how to get from the origin to literally any point you want on that line.
So here's the plan, broken down into 2 super simple steps. Step 1, you got to get on the path. So you travel from the origin to some point you already know is on the line. That's your position vector, A. Step 2, travel along the path. From that point, you just move in the direction of the line. And how far? Well, as far as you want. You can go forwards, backwards, a little bit, a lot. You control that with a little slider, a parameter we call lambda.
Okay, so we've got this intuitive journey idea down. Now let's see how that simple travel plan translates directly into a real, formal, mathematical equation. And there it is, r equals a plus lambda d. So r is just the address of any point on our line. And how do we find it? Well, you take the a vector to get on the line, and then you just add some amount, lambda, of the direction vector d. You change lambda, you just slide right up and down that line. It's really that simple.
The theory is pretty straightforward, right? But the real test is actually using it. So let's run through a couple of classic problems to see this thing in action.
Okay, our first one is about as direct as it gets. They give us a point on the line, and they give us a vector that's parallel to the line. So how do we build the equation?
This is pretty much just a copy-paste job. The point they give us, that's our position vector A. The vector it's parallel to, that's our direction D. You just plug them straight into the formula. So r is our point, plus lambda times our direction. Done.
All right, but what if they don't just hand you the direction vector? In this case, all we have are 2 points, A and B, that we know are on the line.
The game plan here is simple. First, you just pick one of the points to be your position vector A. And honestly, it doesn't matter which one you pick, you'll still get the same line. Second, you have to find the direction. Well, the direction is just the vector that takes you from A to B, right? So we calculate that by doing B minus A. Then you just put it all together like before. Okay, here's another classic you'll see all the time. We've got one line, L1, and we need to find the equation for a second line, L2, that we know is parallel to the first one and goes through a specific point, A.
So here's the big insight. If 2 lines are parallel, they have the same direction. It's that simple. So for our new line L2, we already know the direction vector. We can just steal it from L1. And we have our starting point A. That's just point A. Put them together, and you've got the equation for L2.
Now that single vector equation is really neat and tidy. But sometimes it's actually more useful to break it down into its individual components. And this is what we call the parametric form. The whole process is actually pretty easy. You just take that one vector equation and you look at each component, all the i's, all the j's, all the k's, one by one. And that lets you unpack it into 3 separate little equations for x, y, and z. Yeah, it's a very mechanical thing.
You'll notice we often use t as the parameter here instead of lambda, but it's the same idea. The x-coordinate is just the x part of A plus t times the x part of D. And you do the exact same thing for y and z. It describes the exact same line, just in a different way.
So let's just do that with our first example. For the x component, we get x equals 3 plus t times 1. For the y component, y equals -2 plus t times -1. And for z, it's z equals 4 plus t times 1. And there you have it, our three parametric equations.
All right, you've seen the theory, you've seen the examples. Now it's time to get our hands dirty. Let's head over to the practice zone and lock this in with a few quick problems.
First one up. Point A is our position vector A. Vector B is parallel, so that's our direction vector D. You just slot them into the formula. R equals the point plus lambda times the direction. Easy.
Okay, this one is a little different. It's asking a question. We need to figure out the direction of the line through A and B, and then check if it's parallel to that other vector they gave us.
Okay, so step 1, find the direction from A to B. We do B minus A, and that gives us -8, 5, 6. Now for the big question. Is that other vector, 16, -10, -12, just a multiple of ours? Well, let's see. If we multiply our vector by -2, we get their vector exactly. So yes, the lines are parallel.
Okay, let's try an exam-style question. Notice the keyword here. The line passes through a point, but it's perpendicular to a given vector, not parallel. How do we deal with that? So here's a fantastic little trick for 2D vectors. If you want a vector that's perpendicular to A, B, you just swap the components and make the new first one negative. So you get -b, A. That means a vector perpendicular to 2, 3 is -3, 2. And that's our direction vector. So the final equation is just r equals 1, 1 plus t -3, 2.
All right, one last challenge. And again, watch the wording. We don't want the equation for an infinite line. We want it for just the segment between G and H. How does that change things?
Okay, the first part is exactly the same. We find the direction vector GH, which is 3, 4, and we use G as our starting point. But here is the key difference. We have to put a restriction on our parameter t. To get just the segment, we say that t can only be between 0 and 1. Think about it. When t is 0, you're at point G. When t is 1, you're at point H. Anything in between, and you're on the segment. So let's just bring it all back home. When you boil it all down, it all comes back to this one beautifully simple equation. R equals A plus lambda D. You have a starting point to get you on the line and a direction to tell you where to go. That's it. That's the recipe for any straight line anywhere.
And that kind of power leads to a pretty natural next question, doesn't it? If one direction vector is enough to define a line, what might you need to define an entire flat surface, a plane? That's a thought for another time. Thanks for hanging out with me.